So in this lecture, we'll introduce the TensorFlow library. Previously, we saw how we can manually implement gradient descent algorithms in Python, and we saw it was fairly difficult to try and get all of the details right. And it was fairly hard to debug those kinds of algorithms as well if you try it on your own. So TensorFlow is going to be a higher level library to implement things like gradient descent algorithms, which is going to hide and help you with a lot of these difficult details. So TensorFlow, it's a popular library these days. It's often associated with deep learning, but really at its core, it's just a library that simplifies optimization, in particular gradient descent-like optimization problems, just like those we've seen in the previous lectures. So let's try and re-implement the example from the previous lecture using TensorFlow. Okay, so reading the data again is much the same as before. The only thing we do differently here is we first import the TensorFlow library. And again, we're just reading our PM 2.5 data set, and we're keeping the rows of that data set for which the label is observed or not equal to NA. Okay, and we extract features from our data set. Let's make it a little bit more complicated than it was last time. In this case, we'll consider three features: the temperature, pressure, and wind speed as the predictors we're going to use to try and estimate PM 2.5 or air quality. We extract the feature matrix X and the label vector Y. And the first thing we do that's TensorFlow specific is we convert our vector Y to a TensorFlow constant vector. One more little detail is that in TensorFlow, we want to store this as a column vector. That's something that's implementation specific, but you do have to be careful about these matrix dimensions and things in TensorFlow, or you may accidentally end up applying the wrong matrix operations and your solution would not work. Okay, so let's write down the objective. It's much like we wrote down the objective before, but now we're using native TensorFlow operations to write it. So really here, I'm just implementing the mean squared error. So given a feature matrix X, label vector Y, and my parameters theta, what would be the error of making the predictions under theta? So all that's going on here is I'm computing the sum of squared errors, or the mean squared error, by multiplying X by theta using the TensorFlow operation tf.matmul. It's going to give me a vector of errors. I'm then squaring that result, and I'm reducing to the mean, which means I'm just computing the mean of my vector of squared errors. Okay, so next we set up the variables we're trying to optimize. So I have to actually tell TensorFlow those are variables that I want TensorFlow to solve for, rather than constants whose value I already know. So theta might have an initial value, like it might be a vector of zeros, but I'm also telling TensorFlow that vector is a vector of variables that I would like TensorFlow to optimize for me. So here I'm just initializing theta to be a vector of zeros of length k, and I'm telling it it's a variable. Next, there's a few more boilerplate TensorFlow optimizations. I'm telling it what optimizer I'd like to use. This is what's called a stochastic gradient descent optimizer with learning rate of 0.01. And finally, I'm telling it what is the objective I want to optimize. Okay, so I'm telling it what I would like to do is optimize the mean squared error, and theta is going to be the variable that can be modified in order to minimize this. So it's important to note that everything I've done so far is really just specifying the problem. No computation is actually performed yet. Okay, next there's a little bit more boilerplate for initializing the optimizer. The first thing I do is just tell it this is an objective that should be minimized, and I use this TensorFlow function to perform the initialization. And now I can run everything. So to run 1,000 iterations of gradient descent, I just have a for loop that iterates 1,000 times, and I use this run operation given my objective. And I just print out at each step the objective, which is really just the mean squared error. Okay, and if you actually implement this yourself, you may notice it runs drastically faster than my clunky hand-coded implementation that I wrote in vanilla Python. Okay, so once that's terminated, I can print out the results. I have to use a little bit more TensorFlow boilerplate to do so, but it's fairly straightforward. I just print out theta.eval, and that gives me this four-dimensional vector describing my parameters theta naught through theta 3. Okay, so to summarize, in contrast to our manual implementation of gradient descent, TensorFlow took care of many of the most difficult issues. Most importantly, we didn't have to compute the gradients. We didn't have to write out any math. We just had to specify what the objective was, and TensorFlow actually computes the derivatives for us. So this makes it very easy to experiment with different models. Normally, if you're writing the code by hand, every time you make a small change to the model, you'd have to recompute the derivatives and rewrite the code for those derivatives. In TensorFlow, all of that's going to be done for you. Finally, it's very fast. I mean, even on a simple laptop, this took just a few seconds compared to my manual implementation, which was orders of magnitude slower. If you have GPU acceleration, it's going to be even faster. Okay, so that's just one example of a library that can be used for this type of optimization. There are several alternatives which essentially try and do the same thing. Some popular examples are Theano, Keras, and Torch, whose links you can find here, where you can find out a bit more about the relative advantages and disadvantages of each. Most of them really have quite similar functionality, but there'll be some differences in their interfaces. So to summarize, in this lecture, we introduced the TensorFlow library, which is really just a library that can help you implement gradient descent algorithms. Of course, it can do much more. It can implement very complex techniques like all kinds of neural networks, but really all it's doing at its heart is helping you to automatically compute derivatives and solve these kinds of optimization problems.